Welcome to this series on semiconductors. We will continue our discussion on the doping process.
Pure silicon is a miracle of nature, but for a long time it had a fatal flaw. At room temperature, it is practically useless. A poor conductor that is too sensitive to heat to power a calculator, let alone a supercomputer. So how did we turn this stubborn material into the brain of every device you own? The answer sounds like a mistake. We poisoned it. In the world of physics, we call this doping. And today, we are going to see how adding just one impurity atom into a million can change the world of electronics forever. As we have seen, intrinsic semiconductors are limited. They have very few charge carriers, that is, the traffic of electricity. By doping or intentionally adding specific impurity atoms, we solve this limitation. It's not just about making it more conductive, it's also about the control. We are essentially programming the material's electrical properties. This control gives us four game changers. 1. We multiply the charge carriers, which are electrons or holes. 2. We choose the type of carrier we want. 3. We make conductivity stable across different temperatures. And the last and the most important one, we make the PN junction possible, which is the DNA of every transistor ever made. So what are these desirable impurities? Since silicon and germanium are tetravalent, meaning they have 4 valence electrons, we use 2 specific types of dopants to break the perfect balance. First, the pentavalent dopants from group 15 of the periodic table, elements like arsenic, antimony, or phosphorus. These have 5 electrons, bringing an extra electron to the party. Second, the trivalent dopants from group 13 of the periodic table, elements like boron, aluminium, or indium. These have only 3 electrons, creating a vacancy or a hole. Here is the part that still feels like magic. In the doping process, an impurity atom replaces a semiconductor atom in the crystal lattice. But the scale is tiny. We are talking 1 part per million, 1 ppm. Imagine 1 grain of salt in a giant bag of sugar. That tiny addition is enough to increase conductivity by thousands of times. It is a reversible process and it is precise. And this doping process can create 2 distinct types of extrinsic semiconductors, an N-type semiconductor and a P-type semiconductor. But what happens at the atomic level when these impurities are added? And what are these 2 types of extrinsic semiconductors? We will explore more on these in the upcoming videos.
Thank you for watching this video. For more such videos, press like button, comment, and subscribe to Intuition channel.